Have you ever wondered how tanks, bulldozers, and excavators glide over mud and rocks without getting stuck? And how these massive rigs manage to move from one place to another without any external assistance? If you've observed closely, most heavy machines in mining and construction aren't wheel-mounted, they operate on track system. Yes, you got it right. It's the track system that makes it possible for these massive machines to move effortlessly across mud, sand, water, and even the most uneven terrain. Unlike wheels, which can easily get stuck or lose traction in such harsh conditions, tracks provide a large contact area and excellent ground grip. That's why they're the go-to choice for operating in extreme environments like mining fields, rugged construction sites, and other hazardous terrains where wheels simply wouldn't survive. These track systems are built to be incredibly tough, reliable, and capable of taking on some of the most challenging surfaces on Earth. In today's video, we're breaking down all the key components of a track assembly. We'll explore the design, materials, and applications of each part in detail. So sit back, relax, and get ready for a comprehensive technical deep dive. If you want to know about various names of track system and why they are named so, please click on the link provided in the description. However, before doing that, please watch this video till the end to learn about all the important components of track system. Please subscribe and stay tuned for more in-depth insights into the world of powerful machines and smart engineering. Tracks, also called continuous tracks or caterpillar tracks, are like belts made of linked metal plates. They wrap around wheels and rollers to move the machine forward. They spread the machine's weight over a large area. That's why these heavy machineries can exert less pressure per square inch than your foot. Tracks revolutionized construction, farming, and military vehicles, making the impossible routine. Let's break down the track system. The track is a chain of metal plates or shoes linked by heavy pins for flexibility and strength. The driving sprocket, powered by the hydraulic or electric motor, moves the track system with the help of a track chain. At the front, the idler wheel retains the tension in chain. Rollers underneath support the machine's weight, while top rollers guide the track's return. Every part works together for smooth, unstoppable motion. Let's take a closer look at each component. First on the list is track shoes. These are wide, heavy-duty metal plates that make direct contact with the ground. They are designed with grousers, raised ribs to grip soft soil, mud, and snow, providing traction and preventing slippage. Track shoes distribute the vehicle's weight over a larger area, reducing ground pressure and preventing the machine from sinking in soft terrain. As track shoes directly contact the ground, they need to handle abrasion, impact, bending, and corrosion in harsh environments. Most heavy-duty track shoes are made from manganese steel, also known as Hadfield steel, which contains around 12 to 14% manganese and about 1% carbon. This steel is unique because it work hardens under impact, making the surface 3 times harder without becoming brittle while the inner part remains tough, allowing the shoes to resist wear without cracking. For many applications, alloyed cast steel is used, where elements like chromium, molybdenum, or nickel are added. This helps balance wear resistance and toughness while allowing complex casting of track shoes with integrated grousers. On lighter machines like agricultural crawlers, medium carbon steel around 0.4 to 0.5% carbon is used, which is heat-treated to increase hardness while maintaining flexibility. To extend the life of track shoes, many manufacturers apply surface hardening techniques like induction or flame hardening on the grouser and wear surfaces. This provides a hard outer layer for wear resistance and a tough core to handle impacts and flexing without failure. Track shoes are typically cast for heavy-duty use, forged for high-stress conditions, or fabricated and welded in some specific designs. In modern machines, you will also see rubber-padded track shoes for reducing vibration and protecting paved surfaces in urban environments, while research into advanced steels and carbide reinforcements is ongoing to improve service life in extreme conditions. Rubber pads and poly pads protect delicate surfaces like asphalt. They help distribute the weight of the excavator more evenly over surfaces, reducing ground pressure. Rubber pads significantly reduce noise and vibration, which is particularly important in areas where noise pollution is a concern. The rubber material provides better traction, especially on slippery or uneven terrain, providing greater machine stability and safety during operation. By cushioning the impact and reducing wear and tear, rubber pads and poly pads can extend the lifespan of the equipment, reducing maintenance costs and offering a greater ROI. Bolt-on track pads, clip-on track pads, and chain-on track pads are available. Bolt-on track pads are suitable for machines with pre-drilled holes in the steel grouser shoe, while clip-on track pads are ideal for machines without pre-drilled holes. Rubber track pads and polyurethane track pads are popular options. Rubber track pads provide superior traction and surface protection, while polyurethane track pads offer durability and adaptability. Let's talk about an important feature of the track shoe, the grouser. A grouser is the raised ridge or bar you see on the surface of a track shoe. Think of it like the tread on a tire, which is designed to dig into the ground and provide traction. Without grousers, the tracks would simply slide or spin on soft or uneven terrain. Depending on the application and ground condition, track shoes come with different grouser configurations. A single grouser track, with its high grip and deeper penetration, is perfect for soft or muddy terrain, offering maximum traction. Double grousers provide a balance between traction and maneuverability, often used in mixed ground conditions. And triple grousers, with their broader surface area, are ideal for hard or paved surfaces where reduced ground damage and smoother turning are more important than aggressive grip. Now let's move on to the track links. Track links form the backbone of the track assembly, connecting each track shoe together to form a continuous loop around the undercarriage. These links are the individual metal segments that connect together to form a continuous chain, commonly referred to as a track chain. Track links are typically made from high-strength alloy steel that is heat-treated to achieve a hard, wear-resistant surface while maintaining a tough core to prevent cracking. Each link has pin and bushing joints that allow the track to flex around the sprockets and rollers. The pins connect the links while bushings act as bearings, rotating around the pins as the track moves. Over time, pin and bushing wear leads to track stretch, requiring track adjustments or rebuilds to maintain proper tension and prevent derailment. Some heavy-duty track links are designed with sealed and lubricated or salt systems, where the pin and bushing area is sealed and filled with lubricant during assembly. This greatly reduces wear, extends service life, and minimizes maintenance in harsh working environments. Manufacturing methods typically include forging and precision machining to maintain dimensional accuracy for proper fit and alignment with the sprockets and rollers. Now let's look into the rubber tracks. Rubber tracks are a modern alternative to traditional steel tracks, especially in compact and mid-sized excavators. These tracks offer a unique blend of flexibility, reduced ground damage, and smoother operation, making them ideal for specific environments and applications. Rubber tracks are continuous bands made from high-durability rubber compounds, often reinforced internally with steel cords or fabric. Unlike steel tracks, which have multiple metal segments linked by pins and bushings, rubber tracks are molded as a single piece. This design minimizes vibration, noise, and wear on paved or delicate surfaces. A typical rubber track is made up of 5 key components, each with a specific role. First, the outer rubber tread. Made from a high-durability rubber compound, it's the only part in contact with the ground. Its tread patterns provide traction, channel mud and water, and reduce slippage on soft or uneven terrain. Next, we have the steel reinforcement cables. These high-tensile steel cords run continuously throughout the track loop. Their job? To resist stretching and maintain structural integrity as the machine moves and turns under load. Between the tread and the core, manufacturers add reinforcement fabric layers using materials like nylon or Kevlar. These help distribute stress evenly across the track and improve resistance against tearing or punctures. On the inside, there's the inner rubber layer designed to interface with the undercarriage components, the rollers, idlers, and carrier wheels. This layer absorbs vibrations and supports smooth, low-noise operation. And finally, we have the drive lugs, molded rubber segments on the inner circumference. These precisely engage with the drive sprocket to convert hydraulic motor power into forward motion. The performance of a rubber track depends on several design parameters: track pitch, the distance between drive lugs; track width, which controls ground pressure; and lug geometry, which affects traction and wear. Sidewalls are reinforced to resist lateral cracking, especially during sharp turns or side loading. Rubber compounds are engineered for high abrasion resistance, UV stability, and tear resistance to cope with both hot climates and rugged terrains. The construction process is precision-based. Steel cords are wound into a continuous loop using CNC machines. Rubber and fabric layers are then assembled in a steel mold. High-pressure vulcanization bonds all materials together, forming a seamless, monolithic track. So, why choose rubber tracks? Here's why. They protect delicate surfaces like lawns, driveways, or pavements. They're quieter and reduce vibration for better operator comfort. They're lightweight, easy to replace, and cost-effective for lighter jobs, but they're not perfect. On rocky, abrasive terrain, rubber wears out faster. They also don't handle heavy loads as well as steel tracks. So, if you're in mining or heavy-duty excavation, stick to steel. Next is sprocket wheel. The sprocket wheel is the component that drives the track by engaging with the track links or bushings. It is responsible for transmitting engine power to the track assembly, enabling the machine to move. Typically mounted at the rear in bulldozers and excavators, or at the front in some specialized machines, the sprocket wheel rotates as the final drive turns, pulling the track along with it. Structurally, a sprocket wheel consists of a hub and teeth that are precisely machined to engage with the holes or bushings in the track links. Unlike gears, sprockets do not mesh directly with other toothed wheels. Instead, they interface with the chain or track. The sprocket is typically mounted on the final drive shaft of the undercarriage. The final drive, often composed of a gear reduction system, multiplies torque from the hydraulic motor or transmission. As the sprocket rotates, its teeth push against the track pins or bushings, causing the entire track to move forward or backward. The working environment for track sprockets is extremely harsh. They are characterized by high loads. They face frequent shock impacts. There will be abrasive materials like gravel or sand every time. Also, they need to face constant exposure to mud, water, and dust. For these reasons, sprocket wheels used in tracked systems are typically made from high-strength carbon steel or alloy steel. To enhance durability, the teeth are heat-treated or induction-hardened to resist wear and chipping over prolonged use. The hub and core may remain softer to absorb shock and prevent cracking, while the outer tooth surface is hardened for contact durability. Unlike sprockets used in chain drives or conveyors, track sprockets deal with much larger forces and require robust design considerations. They must match the pitch and width of the track precisely to ensure smooth engagement and minimal wear. A misaligned or worn sprocket can cause premature failure of the track components and reduce the overall efficiency of the undercarriage system. Track sprockets are often designed with self-cleaning grooves or open patterns to shed debris, preventing buildup of mud or rocks that could otherwise jam the drive. Some machines use segmented sprockets for easier maintenance, allowing worn segments to be replaced without dismantling the entire drive assembly. Up next, the track motor. This is typically a hydraulic drive motor integrated into the final drive assembly on each side of the machine. Its job is to convert hydraulic energy into rotational mechanical energy, driving the sprocket wheel, which in turn moves the track chain. Most modern tracked vehicles use axial piston motors or orbital hydraulic motors. Pressurized hydraulic fluid from the main hydraulic pump is routed to the motor via travel control valves. The motor rotates based on fluid pressure and flow direction, which determines the speed and direction of track movement. The hydraulic motor is coupled with a planetary reduction gear system to multiply torque. This combination reduces speed and increases torque, making it suitable for heavy-duty traction in rough terrains. The motor turns the sprocket wheel, which engages with the track links and pulls the track around the undercarriage. This enables forward and reverse motion. Some new generation machines like hybrid dozers or electric excavators use electric motors instead of hydraulic motors for track drive. These provide lower maintenance, regenerative braking, and cleaner energy profile. Up next, the idler wheel. In a tracked vehicle, the idler wheel is positioned at the opposite end of the sprocket. Unlike the sprocket wheel, the idler does not drive the track. It serves as a guide and tensioning point. Its main function is to maintain proper alignment and tension of the track chain as it loops around the undercarriage. As the track moves, the idler wheel ensures it runs smoothly along its path, reducing derailment and excessive wear. Most idler wheels are mounted on a sliding mechanism or a spring-loaded recoil system, which allows them to move slightly forward or backward to automatically adjust track tension based on load and terrain conditions. This dynamic adjustment is crucial for absorbing shock loads and preventing slack, which could lead to chain jumping or misalignment. Idler wheels are typically made from high-strength steel, and often feature hardened rims or replaceable wear rings to endure constant contact with the track links. Some designs also incorporate rubber seals and bushings to protect the internal bearings from dust, mud, and water. Now let's talk about road wheels. In tracked vehicles such as excavators, bulldozers, and tanks, road wheels are also known as track rollers or bottom rollers. They are responsible for supporting the weight of the machine and guiding the track along the lower frame of the undercarriage. These wheels sit between the sprocket and idler, in direct contact with the inner surface of the track chain or the track shoes. As the machine moves, the road wheels roll along the track, distributing the machine's weight evenly and allowing smooth, stable motion over uneven terrain. Road wheels are typically mounted on bogies or swing arms, especially in machines that require suspension or ground contouring. They are constructed from high-strength steel and often feature hardened surfaces or replaceable rims to resist wear from constant metal-to-metal contact and the harsh operating environment. Internally, road wheels contain sealed bearings or bushings, and are often lubricated for life or equipped with grease ports for maintenance. In muddy or abrasive conditions, proper sealing is critical to prevent contamination and premature failure. The number and spacing of road wheels depend on the size and weight of the machine, with heavier machines using more wheels to distribute the load more effectively. Next comes carrier rollers. Located along the top of the undercarriage, these rollers support the upper section of the track as it returns from the idler to the sprocket. While the bottom road wheels carry the weight of the machine, carrier rollers prevent the top portion of the track from sagging excessively, ensuring smooth track circulation and proper alignment during operation. This is especially important in longer track systems, where the unsupported weight of the upper track could lead to increased friction, wear, and the risk of derailment. Carrier rollers are typically smaller and fewer in number compared to road wheels, and they are usually made from high-strength forged steel. Their surfaces are hardened to resist wear from metal-on-metal contact, and the internal bearings are sealed to protect against mud, dust, and moisture. In demanding environments, maintaining the carrier rollers is essential to reduce drag and prolong the life of both the rollers and the track chain. Next, the track frame. The track frame is the primary structural component of a tracked vehicle's undercarriage, serving as the foundation that supports and aligns all other track system parts. It connects directly to the main chassis or swing frame of the machine and houses critical undercarriage elements such as the sprocket, idler, rollers, carrier rollers, and the track tensioning mechanism. The track frame is designed to handle the full operational load of the machine, including the weight of the vehicle, the dynamic forces of movement, and the impacts from rough terrain. It is typically constructed from heavy-duty steel sections or castings to provide high rigidity, durability, and resistance to bending or torsional stress. In many machines like excavators, the track frame is part of a modular or X-frame assembly, allowing flexibility in design and easier maintenance. Some designs also feature sealed compartments or internal wear strips to enhance strength and extend service life. Additionally, the track frame plays a vital role in track alignment, ensuring that the chain runs smoothly between the sprocket and idler without deviation. Finally, track guards. Track guards, also known as track guides, are protective components mounted on the track frame that help maintain proper alignment of the track chain as it moves around the undercarriage. Their primary function is to prevent lateral movement or derailment of the track, especially when the machine operates on uneven or sloped terrain. As the track chain passes over the rollers, sprocket, and idler, it can shift side to side due to ground pressure, machine turning, or wear in the undercarriage components. Track guides physically limit this side-to-side motion, ensuring the track stays centered and properly engaged with the sprocket and rollers. They are typically made from hardened steel or abrasion-resistant alloys, built to withstand heavy contact with track links. There are different types of track guards, including center guides that fit between the links and full-length guards that run along the inside of the track. Some machines also use bolt-on or replaceable wear inserts for easier maintenance. In harsh working conditions like mining, demolition, or forestry, where debris and uneven loads are common, track guards are essential for reducing wear, minimizing maintenance, and extending the life of the track.